Oh.
Principal component analysis. वैसे ही बनाते बच्चों के नंबर ना होते जान बुझ के।
Yes, Amber. With all. Hello. Amber, you sent me one question regarding that different numbers of quantization levels to different frequency components of a signal according to their information content is known as. So I checked with the team. They're telling this second answer is correct only. They have to change the answer.
Okay, ma'am.
Sample zip encoding, yes.
Yes, yes, ma'am. Ma'am, am I audible?
Yes, yes.
Okay, ma'am. Yes, ma'am. I'm heard that, ma'am. Okay, thank you, ma'am. Ma'am, the answer should be, ma'am, Lampelsive encoding.
Yeah, they will change that.
Okay, ma'am. Okay, ma'am. Thank you, ma'am.
So you are registering for the exam? You have registered for the exam?
Yes, ma'am. Actually, na, this subject will be considered for grading in my current semester. So,
Okay.
yes, ma'am. So it's important for me, to like get good marks in like assignments, because we are not getting, ma'am, good marks, like, no, the assignments were not that scoring.
Okay, okay. So when is your week 9 assignment submission?
Ma'am, week 9, I think its submission is, I think it's due on 25th September 2024.
23rd September.
Actually, yeah, ma'am, I have submitted the assignment. Ma'am, there was like but one question in which I think now the correct option, they all were not present there, ma'am. Like, ma'am, if like after the submission the answer key comes, like if the correct option is not available, will all
Then
the students
yeah,
get
we
marks?
can raise
No?
we can raise query with them. They will accept it. Not a problem.
Okay, ma'am. Okay, ma'am.
Ah, so
Thank you, ma'am.
actually, this ninth week was based on the cardinality signal space,
Yes,
then
ma'am.
the energy of a signal, then what is low pass, band pass signals
Yes, ma'am.
was based on that. So today we'll be seeing from that perspective, and then some Fourier series, Fourier transform if the signal is real, and what will be the Fourier transform and their phase transform. So I think
Yes, ma'am.
this week will be bit easy for you
Yes,
to
ma'am.
go through it. It closely resembles this digital signal processing.
Yes, ma'am. Yes, ma'am.
Second is
Yes, ma'am. Okay, ma'am. Thank you, ma'am.
So yes, basically, we will start from the basic and then we will solving the week 9 questions, the last year questions. So as we all know what a signal, and we saw also in MATLAB, how can we represent the signal. Today also we will see some practical examples of low pass signal, band pass signal, and Fourier transform, so that we can actually deal with it. So it is actually a representation of physical quantity, which can be either sound, temperature, or intensity. So basically, signal means anything, any physical quantity that varies with some independent quantity. That independent quantity can be time or space. So there you will have some y is equal to some function of either time or space. So this is called a signal. So this physical quantity can be sound, temperature, or anything. So in practice, what we have as a physical quantity, we generally have a signal. Signal in the sense that suppose temperature varies in terms of sign. So that can be the sign signal. So it is actually a single valued function which carries information by means of amplitude, frequency, and space. So for example, we have voice signal, video signal, and signals on telephone wires. So how the signals is written. So it is represented by the amplitude. This is frequency and this is phase. So A sine omega t plus phi, okay, and that is equals to A sine 2 pi ft plus phi, where A is a peak amplitude, F is a frequency, and phase phi is a phase angle. Now, angular frequency is nothing but W is equals to 2 pi F, where F is a linear frequency. So this is simple signal system overview. So signal with different phases, amplitudes, and frequencies. So you will have, suppose, amplitude, this is peak amplitude, okay, and this is the different amplitude. Different amplitude is there. Signal with the high peak amplitude, signal with low peak amplitude. Now you have phase. So what is the difference between phase? So this is 0 degree, and if you shift by 90 degree, so it will shift by 90 degree, and if you shift by 180 degree, so again the 180 degree will be like this. But how 180 degree will be shift? Like this one completely shift like this, 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 so that opposite signal will come. Similarly, if you have different frequency, so how different frequency works? So this is having some frequency of 1 hertz. So sorry, 12 hertz. So if you decrease the frequency, you will have more space. And if you increase the frequency, you will have less space. Okay. Now classification of signals. So in practice, we have one-dimensional or 1D signals. If the signal is a function of only one variable, or if the signal value varies with respect to only one variable, then it is called one-dimensional signal. For example, audio signal, biomedical signals, temperature signal, in which the signal's function is a function of time. As we can see here, audio, this is different type of signal. This is what type of signal? This is biomedical image, this is ECG or something. Okay, and this is temperature. Okay, now 2D signal. If the signal is a function of two variables, so whenever we all know what is random variable. So random variable is nothing but a variable that maps the outcome of any random experiment to a real line. Okay. Now, when the random variable becomes a function of any other independent quantity, that is time and something, that is called random process. So now, similarly, we can represent the simple signal by the random variable, but when it comes to the different characterization or different 2D signal, then we can call it as a random process. That also we will see in the MATLAB. Okay. Now suppose image signal in which the intensity is a function of two spatial coordinates, either x or y. Similarly, 3D. So if the image is a function of three variables, or if the signal value varies with respect to three variables, then it is called three-dimensional signal. For example, like this. So you can have x, y, and third is intensity. Okay. Now, with respect to nature of signal, now we already saw this is the normal classification with respect to dimensions. Now, with respect to nature. So, nature in the sense it can be continuous time or digital time. Here only the concept of digital communication or DCM digital communication modulation starts. Okay, we will see. So if the signal value uh, continuously varies with respect to time, then it is called continuous time. Okay, or analog signal. So all physical occurring signal that we see in practice is all are analog in nature. So it contains infinite set of values and it represented as shown below. This is continuous time. Okay. Now digital signal. If the signal contains only two values, then it is called digital signals. Why only two values? How this continuous time signal converts to digital time signal? When continuous time signal discretized, discrete in time, uh, as well as amplitude, then it becomes digital signal, not discrete signal. Remember this. Okay, this is digital signal. Like it will be discretized in amplitude as well. It will be discretized in time as well. Okay. Now, if the signal contains discrete set of values with respect to time, it is called discrete. Suppose you'll have like this, then it is discrete time signal. It contains finite set of values. Sampling process converts continuous time to discrete time. Now, first you have input as a continuous time signal. Then you pass it to sample and whole circuit. Okay. Then you pass it to sample and whole circuit. Sample and whole circuit is nothing but a switch. It will act just as a switch. Then what you will have? You will have discrete time signal as output. Now, when it passed to a quantizer, which act as a approximation, then you will have as digital signal. So, and sometimes it is also referred as these two blocks as A to D converter, analog to digital signal. Because in practice, we don't have a digital signal, but we deal with all the devices inside the devices, in fact, the phone, everything, and with digital signal. Okay, the phone also have the encoder, is analog to digital converter that converts the physically occurring signal to a digital signal. Okay, now we know what is different type of signal according to their nature. Now, representation of discrete type signals. So discrete time signal is actually a function of integer number n. And in discrete signal processor, the signal is represented by a discrete encoded values with a finite precision. So like this, okay, xn equals to 1 for suppose n equals to 1, 2, 3. Like this we have to write. And it is sometimes written as like this, infinite duration and the finite duration you can write completely. Okay. Sometimes it is also known as mathematically discrete time signal can be determined by, okay, when you have continuous time signal as an input. This is continuous time signal. When t equals to n, t, n is a discretization in time domain, and this is a period. Okay, then it becomes a discrete time signal. Now, basic types of signal, as we all know, but still I'm just giving you the brief overview. Unit step function is denoted as 1 when t greater than or equal to 0, and 0. What happened? Someone joined. Oh, so the unit step function is denoted by ut and it's just used as a best test signal. Area under unit step function is always 1. Why area under unit step function is always 1? It's not only unit step function. The area under any probability distribution function is 1. Okay, this is PDF of unit step function. So this shows us minus infinity to infinity, ft dt is equals to, where ft can be ut or rt, anytime. Unit impulse function. So this is very great. The unit impulse function is denoted by del t, and it is defined as 0 for t not equal to 0 and infinity at t equals to 0. But area under del t also 1. Okay. Okay. So actually, the area will be calculated as 1, uh, the value itself is unit step function is value is the unit is having the value as ut, right? So that's why when we integrate from any function, so it will become different other function. So it is ut. So ut, because it is having all the values as 1. Okay, if we integrate del t, it will be having ut, and if we differentiate ut, will have del t. That's why? Because ut has Laplace transform of 1 by s, and del t has Laplace transform of 1. So when you integrate this del t, so integration is nothing but a multiplication by 1 by s. So that is ut. And differentiation is nothing but the multiplication with s. S is nothing but e power j omega. I don't know whether you know Laplace transform or not, but leave it. But similarly, if you want to have unit pulse, so pulse will be having this area as 1. Okay. Now ramp signal. If you integrate ut, you will get the ramp, and it is having the Laplace transform 1 by s. Ramp is nothing but for t greater than or equal to 0, it is t. Otherwise, it is 0. Now parabolic function. Again, it will having the other property, t square by 2. Okay. Signum function. That is very strange and good. We'll have uh, 1 if it is greater than 0. 0 minus 1, it is goes to 0. And if 0, it's 0. So this is one of the odd signal. So again, I will just differentiate between what is odd and even. So even signal and odd signal. You'll have xt equals to x of minus t, and xt equals to minus x of minus t. Okay, and remember, and x0 is equals to 0. So this is following. So this is odd. Can you give me the example of even signal? Cos. Cos is even signal. Sine is odd signal. Okay. Now another type of signal is exponential signal. I'm just leaving it. Rectangular signal. So please remember the notation of this rectangular signal. This is represented by A R by T. Okay. What does it represent is you have this period as T, or the width is T. A rect R by T having A as a area, this amplitude, and minus T by 2 to T by 2. Similarly, triangular signal you have like this, and it is represented as A1 minus mod of T by T. How? How? Because let's plot this. What is this mod of T? Okay, mod of T is nothing but this one. Okay. Now minus. So minus mod of t is nothing but minus mod of t is nothing but this one. Yeah. Yes. Minus mod of t is nothing but this one. Now 1 minus. So you're adding plus 1 to it. Okay. Divided by t. Let's divide by t. So somewhere it will come like this. Somewhere it will come like this 1 by t. Because it is multiplied with 1 by t. Because previously minus 1 by t was like this. And if it's multiplied with some amplitude, it will come like this. Now, if you are adding 1, we are adding 1. So, you'll have some more addition. Okay. Suppose like this. Okay. And finally, you're multiplying by a. So, it is like this. That's why it looks like this. Now, you already know about sinusoidal, cosinusoidal. Now, classification of signal and the following criteria. So we know continuous time, discrete time signal, deterministic and non-deterministic signal. We already know this. Deterministic and non-deterministic we'll see, even odd we'll see, periodic and periodic see, real and energy and power signals we'll see, real and imaginary signals we'll see. Okay. Now continuous time and discrete time. A signal is said to be continuous time. Continuous when it is defined for all instance of time. Okay. A signal is said to be discrete when it is defined at only discrete instance of time, as the name suggests. Not deterministic and non-deterministic. So a signal is a deterministic if there is no uncertainty with respect to its value at any instant of time, or signal which can be defined exactly by mathematical formula that are known as deterministic signal. Like we can determine it, as the name suggests, we can actually determine it, because how we can determine, suppose a xt is equals to a cos 2 pi fct. So based on t value, you will have the x value. Okay, it is following the particular behavior. Similarly, non-deterministic will be random signal, you can't determine that. Okay, so that type of signals are the non-deterministic signals. Now, even odd signals. A signal is said to be even when it satisfies this property. Okay, like this, like this. So this is even signal. Now, and if it is not following that property, it will be odd signal. Okay, odd is this. One more thing is x0 is equal to 0. And a signal is said to be periodic when it follows this periodic nature. Okay. Energy and power signals. Again. So when a signal is non-periodic, then it is called energy signal. When the signal is periodic, it will be called power signal. Okay. That's why we are calculating power as 1 by 2t, or integration over one time period, or integration over one time period, square of dt, limit t tends to infinity. Okay, means it is periodic in nature, that's why you can do power. Now, what will be power of energy signal? And what will be energy of power signal? Anyone? So this is the answer. Power of energy signal is 0 and energy of power signal is infinity, because power signal is actually periodic in nature. So it will infinitely have many values, and it will tends to infinity energy. Real and imaginary signal. A signal is said to be real when it satisfies this property. Xt is equals to x conjugate t. And when it is odd, when it satisfies this property. xt equals to x of a signal is said to be real is this one, and it is said to be odd in this one. Again, for a real signal, the imaginary part is 0. Similarly, for the imaginary signal, the real part should be 0. So this is actually imaginary odd. Okay, this is real even. Don't be confused with the real odd previously. Okay, the basic operations of signals. So we can have amplitude scaling, simple amplitude, as we all know. When it comes to addition or subtraction, okay. So what do you mean by addition and subtraction? So if we add these two signals, so it will come like this value, this value, this value, this value. This because we are adding. Now, if you subtract it, okay, so this is coming negative, this is coming 1 minus 2, this is minus 1, like this. Simple, simple, very simple. This is multiplication. You're multiplying directly. This is interesting. Okay, time shifting and negative time shifting. So in this, we often get confused, like what is time shifting? Okay, so I'll give you a trick. How can we have negative time shift and positive time shift? Sometimes when we are adding here, but still we are calling it as a negative shift because we are advancing that signal. Okay, we are advancing that signal. That's why it is called negative shift. And here we are at negative. That's why then also we are telling the positive signal because we are just telling that we have positive shift. So for the trick I'm telling you, if it is positive, okay, just subtract negative. Suppose this is 5, minus 5, 5, and this is plus 10. So it will go to minus 15, 5 minus 10, minus 5. This will be x t minus plus 10. Again, wait. You have, you have 5 minus 5. So how x t plus 5 will look. Hmm? So you have minus 5 minus 10. 5 minus 5, 0. Will look like this. Okay, I did opposite. It will look like this. It is actually advancing. Time scaling. So yes, if it is greater than 1, so it is compression. Okay, 2t. So it is compression. T by 2, it is actually division. T minus t. Yes. So what I was telling, if it is minus, so it's actually adding it. So if it is minus t naught, so it will go to t naught and 5 plus t naught. And if it is plus, so it is actually subtracting it. So this is wrong. This is wrong. It will go like this. Okay, this is wrong. In both the cases, it can't have the same thing, right? So we know already about compression and expansion. Again, so if the multiplication is greater than 1, so it is compression, not the expansion. So it is acting as opposite. Okay. So what trick I was about to tell you, this if x 80 plus 5, if it is this like this. So for giving you x 80, suppose this is nothing but y. So yt plus 5, nothing but you have to subtract minus y. Okay, 5. And similarly, you have to divide t. Okay, this is compression. This is expansion. My battery is going to 1%, I'll just keep on charging, then we will again start with time reversal. Time reversal, as we all know. Okay. Convolution, then correlation. There are two different topics. Okay. Convolution between two continuous time signals can be written as yt is equals to, and when we have the convolution as an output, or their application when we have a linear system. Yt is equal to xt convolution with ht, isn't it? Just give me a second, I'll keep on this on charging. We'll see some MATLAB, then we'll come back to this. So real-time systems, the functions in a signal processing toolbox in MATLAB enable us to get a deeper understanding of our signals. But what if we want to have more control over the processing algorithms? So this is the signal and this is the processing algorithm. This is the real signal processing toolbox.
If you have a file containing recorded audio, you can process the entire file at once. This is sometimes called batch processing.
So if we have file, we can process the entire file, but this is also called a batch. So,
Because you're processing a batch of previously collected data. But what if your data isn't pre-recorded? Say someone is talking at a live event and you need to process the signal in real time. This is called streaming.
so if we want to process a signal, okay, we don't want to actually take that input and do that. So it is called streaming. Real time thing is called streaming.
To do this, you need to continuously receive and process small segments of a signal without introducing a noticeable processing delay. In MATLAB, we call the segments frames.
So sometimes while we do the image processing also, so images come or the video processing, it will come in the form of frames, like one by one, one by one, one by one, pixel by pixel value by pixel value. So when it is video, it is 3D signal. When it is a image, it is a 2D signal. So the real time processing will be continuously will having the frame, one frame, two frame, three frame, like that.
Let's use an FIR filter as an example. Say that we want to process the signal 4 samples at a time.
Why FIR? Because this is a finite in nature. If you have infinite impulse response, you'll have that loop, and that will act as an infinite impulse response filter.
Here are the first 4 samples, and an FIR filter with 3 coefficients. Recall that when you filter, the beginning of a signal has a transient. Then we get the next 4 samples. If you filter the frames independently, there's going to be a transient at the beginning
Understand this?
of 4 samples, and an FIR filter with 3 coefficients. Recall that when you filter, the beginning
We added 0, 0 in the front, then B1, B2, B3, that is Y1, okay? 0, 0, X1, B1, B2, B3, that is Y1.
of a
Then 0, X1, X2, B1, B2, B3, that is Y2.
signal has a transient.
Then X1, X2, X3, B. This is also reversing, okay? B3, B2, B1, that is Y3.
Recall that when you filter, the beginning of a
B3, B2, B1,
signal has a
B3,
transient.
B2, B1, okay?
Then we get the next 4
Then we are getting the next 4, Y1, Y2, Y3, Y4.
samples. If you filter the frames independently, there's going to be a transient at the beginning of each frame. However, if your system could remember the previous frame, then you'd only have a transient once at the
But whenever we are starting again, we have to have a transient. But if our system remembers that, so only one we will have. At only one time we'll have a transient, otherwise we'll not have.
beginning. When streaming, most signal processing algorithms require remembering previous samples or states. To design or simulate systems like this, you can use system objects from the DSP System toolbox. First, you need to create a source object for your streaming data. To prototype your system, you can generate a sine wave, stream from a file, or use a signal in your workspace. When you create the source object, you'll specify the number of samples per frame. This is the amount of data that you'll process at a time. Then you'll create system objects to do the actual processing, like spectral analysis or filtering. Depending on the type of processing, you can set different object properties. For example, if this was an FIR filter, you might set the numerator coefficients. The results can be stored in sync objects. These are counterparts to the source objects. Then you'll repeat this process for as long as necessary. In this module, you'll use these different system objects to design and implement a frame-based streaming simulation.
So basically, the DSP system toolbox provides you with the system objects to handle the streaming data, that is a real-time data. And the system objects are created by using the standard syntax, that is object handle equals to package.object name. Okay. Since the system objects that you are using in this chapter are from the DSP system toolbox, the package name is DSP. To begin, you will create a signal source object. Okay, that is a signal source object equals to package dot object name. So you can set the properties when you create the system object. For example, here you can set the number of samples per frame. Simple system objects generally have the lot of properties, so you will usually only set the property that are relevant to our application or your application. If you don't set a property, by default the values will be used. Second input sets the number of samples per second. So source suppose equals to DSP dot signal source. You have number of that is signal and number of samples per frame. So this is the second input sets the number of samples per frame. So per frame, how many samples you are having? Okay, so in this way, we can have the number of samples per frame. Okay, so DSP dot signal source with properties, what you would have? First of all, signal. Okay, that is having the type as double, and uh, this is the dimension of the signal. And samples per frame is 1000, and signal end action is set to 0. Now, here the number of samples per frame wasn't specified, so the default value of 1 is used. So if it is not specified, the one it will be used and set is to 0. So as far as we understood from the signal, uh, like this we can create with the DSP toolbox in MATLAB. Okay, now we'll see some practical application. After this, we will read this Fourier series, Fourier transform. We have already seen the classification of the signals so that we can solve the week 9 questions. Okay. So here, let's see some practical examples. So to stream a signal with the DSP system toolbox, you can generate a signal or import one from the workspace with DSP dot signal source with the signal and sample as we can see. So here we have already this load, this is the load monitored fan dot mat. So we can see here what is the properties. Okay, the class is double. The byte it consumes is 8. The size is 1 cross 1. FRO. So this is a property of the signal that is a monitored fan. Okay, and the total number of samples is this 2, 1, 2, this many zeros cross 1. Okay, the second input stamp is the number of samples per frame that you want to import. The frame is one of the portion of the signal. So use monitor as your signal source and specify uh, and name the object. So anyone, so using whose we can see actually. Okay, after loading this, so that is already uh, created. So using whose we can see the properties here in the workspace. Okay, so we have the source equals to, and if you wonder like how can we use DSP, so uh, you have to download the toolbox known as DSP. By default, in every institute, it will be there, but still, if you don't have, you can download this toolbox known as DSP. So, signal. What is the name of signal? Name of signal is monitored fan. And the samples was SAMP. Sample should be already defined here. And the sources was 1,000. Okay. So let's define first as 1,000. Maybe we will require some more. Okay. So now that you have set up a system object, the next step is to turn it on. Okay. We will see frame by frame. Okay. To stream one frame of signal, you can use the object that you just created with empty parenthesis. So again, signal is there with this many frames, with this many samples per frame. So how many samples you have? You have thousands of samples. And this is a real-time streaming. This is not a normal that is a what was the other type of streaming? Anyone? So if you want to see in term perspective of random variable, so random process, right? Again, so read the first frame of data from SRC, name the result as frame. So we have just created the empty parenthesis, the frame, first frame of data. So how can we name the frame? See, we can see that the frame, okay, the first frame of data. Read the second frame of data Name the result frame 2. Don't use a semicolon. You at the end of the command you can just see. So frame 2 equals to SRC. If it's MATLAB starts with 1. Uh, okay, we can just put it as a C. This one. Okay, we can't keep as indices because this is not a matrix itself. Okay, just suppose we want to see this SRC. So SRC is not a matrix. It's just having these many values. So we can't keep one value. Okay. Notice that the data in frame 2 is different. If you want to get the statistics about your signal in the time domain, you can use a technique for generating signal from this operation, use a time scope. So let's use this time scope. It will generate a line plot. Okay, scopes are useful because they contain a built-in functionality like a peak finding. So we'll see the signals variation. Sample rate that is already defined by limits scope frame. That's right. Okay, so the frame that we are seeing as a scope, we are first defining the scope where we have the limit as a y limit, and we are seeing this first frame. So we can see the frame. Uh, this frame, which will as acting as a signal, it is having these peaks. I think, can you tell me, just now we studied the periodic and non-periodic. Can you state this that is a either periodic or power signal, or we will calculate the energy signal? So here the power, can anyone tell me whether the power will be calculated or the energy will be calculated? See, energy will be calculated for the finite signal, okay? But again, that signal should not be periodic. So if the signal is periodic and is infinite in nature, then we have to calculate the power. So if any doubt, you can just to display the spectrum of a streaming signal, you can use the spectrum analyzer system, okay, as an object. To create a spectrum analyzer object named analyzer, set the sample rate to fs, plot as two-sided spectrum to false and method to Welch. So, so create any analyzer equals to spectrum. Okay. Uh, if we are not getting anything, we can just do help. Okay. So display the frequency spectrum. Okay, so it has a scope. Set the sample rate to fs. So where I have to send the sample rate to fs from a plot first method to Welch. Let's see the solution itself. Okay, so it is only having that uh, the methods. So So it means that it is having these values. So view type, spectrum type, this type, method as a spectrum estimation method. This many types are there. So spectrum analyzes sample data as FS, plot two-sided spectrum as false, method as Welch. So let's see. It's not plotting, we'll see that. Filter bank method. In the previous task, you set the spectrum estimation method to Welch method, which is taught in the improving power spectral density estimate module. Okay. By default, the spectrum analyzer uses the method called filter bank. Was this map work YouTube video to learn more about the channelizer based filter bank? Let's see this. So it actually, in general, use the filter bank method if you want to have more accurate peak locations, more accurate noise floor, uh, lower spectrum leakage, better frequency resolution. The filter bank method is slower at tracking the changing frequencies than the Welch method. We have to track actually where the frequency is changing in a Welch method. If you have fast changing signal and don't need the benefit from the filter bank, Welch methods can provide the better results. So
the most common way of doing spectral analysis is the window and FFT combination, but I always use the filter bank method. I'm Ricardo Lozada, a signal processing developer at MathWorks, and in this video, I'll show you why. First, let's get some terminology out of the way. In the context of spectral analysis, combining a window with an FFT is called a periodogram. Averaging periodograms is referred to as Welch's method.
So averaging periodograms means where we used for improving the power spectral density. Okay. Welch methods were used with optional windowing overlap.
If that was too confusing, don't worry about it. Hopefully by the end of this video, you'll just use the filter bank method instead. Now, I will emphasize that whether you're using Welch's method or the filter bank, averaging is important to reduce noise in the spectral estimate. Okay, with terminology out of the way, let's look at the challenges in spectral analysis based on a finite record of data. I'll start by looking at the simplest application of spectral analysis, identifying the frequency of a single sine wave and its power. When we look at a sinusoid's power spectrum, we expect a single line spectrum. The frequency of that line should match the sinusoid's frequency, and the amplitude of the line gives
because sine have the single frequency as we know from the Fourier transform.
Average power. However, if we take a finite segment of that sinusoid, when we compute the power spectrum using an FFT, we will often get something like this instead. As you can see, that's
true power.
That's quite different than what is expected.
This is a 2 power and actually power spectrum of the rectangular window plus FFT.
The peak of the computed spectrum is close to, but not at the right frequency.
This peak should be close to this frequency. That is also known as frequency bias because it is not actually matching.
The peak value is also not quite right.
It is not quite complete, correct. If
And
you zoom it out, this is called, it is not matching, this is called a spectrum leakage.
Lines. If this wasn't test data, it would be hard to tell whether these lines are due to actual periodic components.
So this black color is actually the true power, and this is power spectrum from the rectangular window plus FFT.
Or simply artifacts of the computation. So why are we getting all this spectral leakage? To answer
so from where we are getting the spectrum leakage, the answer is through rectangular window plus FFT.
Let's go through the steps we take to compute the spectral estimate. First, when
this is the amplitude and this time samples.
Dealing with finite segments, we are implicitly windowing the data with a rectangular window. In the frequency,
when we have the finite samples, we are only considering the finite number of samples for the rectangular window.
Domain, this windowing manifests as a sinc function.
And as we know, this Fourier transform of any rectangular function or rectangular pulse is actually the sinc function. Okay, that is a rect t by t, this r by t. So it is having the Fourier transform of a t sinc ft, because t is the width of the signal.
When the window data is sinusoidal, the sinc function is centered at the frequency of that sinusoid. Next, when we compute the FFT,
try to
data is
see this.
sinusoidal, the
Okay.
sinc function is manifest as a
This is
sinc
actually
function.
the gain and frequency. This is not the Fourier transform or the power spectral density. It's just a gain versus frequency.
When the window data is sinusoidal,
Where the window data is sinusoidal having the power as average power with respect to frequency.
sinc function is centered at the frequency of that sinusoid. Next, when we compute the FFT,
so true power spectrum from the rectangular window, this is light gray, and power spectrum of a rectangular window data. This is the power spectrum of rectangular window data.
we are effectively sampling the shifted sinc function at evenly spaced frequency points. That's the actual power spectrum we are able to compute.
And that is only giving the spectrum leakage.
The main drawback of a rectangular window is its poor side lobe attenuation, only about 13.
Rectangular window is having the poor side lobe attenuation of about 13 dB. So this is the drawback of rectangular window.
dB. This causes the appearance of large spectral components where none exist in reality. Keep in mind that zero padding in order to compute more FFT points does not solve the problem.
In fact, zero padding also doesn't help.
In fact, that is what I did to compute the blue line in this plot. The real solution is to have a longer segment length. However, this is not always possible since the data may not be stationary for that long. And anyway, there's a practical limit to the size of the FFTs we can compute. Before moving on, let me mention that there are a few rare cases when things work out nicely. For example, change the frequency of the sinusoid to one of the FFT frequency points and the following happens. Now, we are still windowing, so a sinc is still involved, but it just so happens that the FFT points are sampling the sinc exactly at its peak and at the sinc notches. This eliminates spectral leakage completely, but the odds of this happening are low. The traditional way of dealing with spectral leakage is to use a non-rectangular window because it will have a lower side lobe. Pick your favorite window.
So if we have don't use rectangular window, then we will use a halving window where we have different lobes. Okay, so that it covers the larger segment. But again, one solution, as he told, that we can have the sinusoidal frequencies matching with the Fourier transform frequency.
It will have a defined amount of side lobe attenuation. Let's compare using a rectangular window with using another common window, the Blackman-Harris window, and using the filter bank for the single tone we have.
Okay, rectangular window or Black-Harris window or filter bank for the single tone.
Tried previously. This time we'll use the spectrum analyzer block. To keep things fair, for this and all comparisons, we'll use the same segment length for all analysis methods. So, using a non-rectangular window helped a little, but not nearly as much as using the filter bank.
Filter bank is
when windowing a given segment length, the trade-off for having better side lobe attenuation is a wider main lobe. While better side lobe attenuation is good, a wider main lobe is not. Let me show you why with the second test case. We'll use a different window, but similar results hold for all windows.
See, we have the sine wave of different frequency. Okay. And finally, we are adding and seeing through the spectrum analyzer.
This model shows two tones that are close to each other.
Two tones are close to each other, that is showing.
Different window, but similar results hold for all windows. This model shows two tones that are close to each other. We will once again compare the rectangular window with a different window and with the filter bank. Because of the wider main lobe, the hand window does not provide enough resolution to distinguish between the two tones. Only the rectangular window and the filter bank provide the required resolution. In this case, of all windows, a rectangular window is your best choice. Now let's look at a case where it's not. This model shows a simplified 16 QAM communications link. We're using the spectrum analyzer to visualize the received signal. There is very little noise added in the channel, as can be seen from the constellation plot. Let's once again compare the three methods. The poor side lobe attenuation of the rectangular window is evident, and it gives the false impression that a lot of noise was added by the channel. The Kaiser window and the filter bank are both able to adequately compute the received spectrum. So, when picking windows, we are left with a compromise between resolution and side lobe attenuation. But what if you need both?
Again, we have to just have the trade-off between resolution and side lobe attenuation.
Well, as we just saw, the filter bank method gave good results for all cases. That's why I use it. So how does it work? A filter bank is just a set of bandpass filters each one centered at a different frequency. The idea mimics how old analog spectrum analyzers work, but instead of a single filter sweeping across the spectrum, the collection of filters covers the entire spectrum simultaneously. Average power is computed for the output of each bandpass filter. Now, we want to do this efficiently in order to compute the spectrum in real time. Here's how. The FFT itself can be viewed as a filter bank, just not a very selective.
See, the strange thing is FFT itself is viewed as a filter bank, not just very selective. So we will see that how FFT is viewed as a filter bank.
We can boost the FFT with a polyphase filter to form what is called an FFT polyphase filter bank, or simply a channelizer.
So polyphase filter as a channelizer.
Convert this filter bank corresponding to just an FFT into this much more selective filter bank. The channelizer starts with a prototype narrow low-pass filter. The role of the FFT is to efficiently modulate the filter to cover all frequency bands. Let's look at frequency leakage from the filter bank perspective. Start with just the FFT. The filters are centered across different bands and overlap significantly except at the center frequency. This overlap is what causes leakage, since signals at such frequencies get through multiple filters. Only around the center frequencies of the filters, the overlap is minimal and there's minimal leakage.
Okay, I think that is enough for us. Change the spectrum analyzer from the previous tab so that the spectrum estimation method is a filter bank instead of filter. So, method to filter bank. Nice. So we can see frame one. You can use the system object just to create it like a function. Okay. Spectrum analyzer and then variable name as data. Use analyzer to display the spectrum estimate. Spectrum analyzer will display a pop-up. We need to edit the split close spectrum analyzer first. Okay. So the first frame of signal has already saved in the variable name data. Use analyzer to display the spectrum estimate. So this is gain, this is frequency. Now you see the spectrum estimate at the first frame of the signal, that is this one. To pass more data to the spectrum, use analyzer with multiple frames that you can see. For example, this code updates the spectrumizer with 3 frames. Call with this. We can again change the method to Welch. This is taking time. So you have already designed your filter. If you have the transfer function, so that the linear system that we generally see as a before the output of the convolution of any system, that is also called transfer function when it is there in the Fourier transform. Okay, so HT when it's converted to Fourier transform, that is HS, capital HS, that is called transfer function. You can filter a streaming signal using the coefficient vectors. So you can get those coefficients on a digital filter with the TF method for a design field object. Okay. Their transfer function is D. Okay. BA. BA will be the coefficients. You can get these coefficients from the digital filter. So this is a filter. So let's have the coefficients as BA. So this is the coefficients. See, the coefficient A is 1 where the B is having a size of 1 cross 238. Do you wonder how? Think about it. So now you can make the FIR filter using the system object. This is FIR filter, DSP dot FIR filter using B. The first input to the DSP filter sets the numerator coefficients. Okay. If you're using the IIR filter, you have to set the numerator as well by using the two inputs. So let's create this FIR. FIR is equals to DSP dot FIR filter. See, it is showing the direct form. You have two type of structure, like direct form 1, direct form 2. And numerator sources property. To use the filter, your filter object can be used as a function. For example, if your filter object was called myfill, then you would filter with out equals to myfill dot in. Okay. So you have the data as data filled, and data automatically getting stored in the name the output as data filled plot also my filled this data. Oh, solution. Where I'm doing wrong. FIR, my field. So sorry. FIR is my filter, right? FI field is not there. FIR. So you can see the filter transient at the beginning of the signal. Repeat the code from task 3 on the next frame of the data. Only the plot will be created. Again, data field. Is the plot correct? Oh, plot FIR source because it is written as a source. So FIR, okay, source data, as we know, the data can be written as source s- empty parenthesis. So it is source empty parenthesis. That's it. The second frame of data no longer has a filter transient. See, It is not having the filter transient. It is having the transient, okay? But it is not having the filter transient. While you're streaming a signal, it remembers the previous block. That's fine. No transient. Because first time only it will require the transient. Otherwise, it is remembering because the DSP component blocks are made such like that. While you are streaming a signal, it remembers the previous block. In this activity, you got each frame of the signal by manually calling SRC repeatedly. In the next session, you'll set up the loop to automatically process the signal. First, in the next activity, it will create a metric to use in the loop. It's fine. I think my tablet will be charged. We'll go back to the signal processing concepts. Just give me a second. Yeah, so my tablet is taking some more time, so we can do some practice here only. Then we'll go back. Meanwhile, it's fine. So in this project for designing digital filter, you can create a metric that finds the fans, okay, that have an outer race fault. The metric will detect the fan issues when the power spectrum looks like the plot below. Okay, broken outer race and like that. It didn't got saved. Internet is okay, we saw all these things. Multiplication and compression, time shifting. We were seeing this convolution before that it came. So when convolution is called, that is used for output of any LTI system. And you have ST, XT. And this you will get as out. The formula is X tau ST minus tau D tau. But when correlation is called, it is used by similarity between two signals. If it is XT by T, then XT, this is similarity YT, is equals to minus infinity to infinity XT by T minus tau. Formula is minus infinity to infinity XT YT minus tau dt. Here d tau is there. Here dt is there. So x tau y t minus tau t t. Where d tau. That is very good. So if we say what is system, moving to system. So system is a device or the combination of devices which can operate on signals and produces a corresponding response. Input to a system is known as, also called as excitation, and output is also known as response. Okay. For example, the communication system. You have this. Now again, the property of system comes linear, non-linear, time variant. Is these things we will see now, just now. So if it is linear, what does this mean? You will not have the order change. It's non-linear. So basically, you'll have the superposition and homogeneous properties with the linear system. Is it linear? What do you think? So you have to just first check A x t plus A2 A1 x1 t plus A2 x2 t should lead to A1 y1 t plus A2 y2 t. What does this mean? This means if xt is leading to yt and if this is also leading to this one, then this means that the system is linear. Otherwise, it is not linear. Not time varying. Okay. So when you have xt as out system leading to this yt, suppose xt plus t naught is leading to yt plus t naught plus minus or whatever, then it is time invariant. Memoryless and static. Okay. Static system is memoryless, whereas dynamic system is a memory system. It means it can store some value. It can remember something. Okay. So for example, yt is equals to 2xt. For present value yt equals 0, the system value is again this output is only dependent on these things. So this is memoryless or the static. It is static depending on the only that time. And if the output is depending on the previous output also, previous time also. So it is having the memory. What does this mean? Memory means you have system. Okay. xt, and this is causing some delay. Z power minus 3. So this yt is nothing but xt plus xt minus 3. Then it is called a dynamic or with memory system. Again, cause and non-cause. So a system is called as a non-cause. Causal means a normal system that actually exists. Non-causal system doesn't exist. Non-practical system means if it is an input, the output of a system depends on the future input. Is it possible? No, never. So that type of system is not causal. So this is depending on the present or the past. So it is possible, yes. But if it is depending on the future, is it possible? No. So it is not possible. Non-causal. Again, invertible, non-invertible. So a system is said to be invertible if the input of the system appears at the output. Means you can actually, by seeing the input or by seeing the output, you can just generate the input as well. So how come? If it is just a multiplication, if it is a system that is can multiply with the previous system, that will be the invertible. For example, y is equals to xs multiplication with h1s into s2s. S2s is this one. System is invertible. If xt not equals to y, not invertible, not required for you. Stable and stable is very important for you. I was telling about the correlation and the convolution. This is the convolution, x tau, d tau. Correlation was what? If we do the summation with respect to so let me tell you what is correlation convolution. This is having the formula as minus infinity to infinity. X tau, ht minus tau, d tau. When correlation happens. Okay. So this is having the formula of xt h tau minus t dt. And if it is discrete, it will be replaced by sum. and this is K. Okay. What you're doing, you're replacing T by tau. That's it. In convolution correlation. Their practical implementation is what? There's some properties. If you're doing the convolution with T minus T naught, so here we are talking only about the convolution. So the system, the signal will also replaced by T minus T naught. Because there is a property. Again, this is only possible with respect to delta. This is written wrong. This is delta. So convolution of two causal sequence is causal. Convolution of two anti-causal sequence is anti-causal. Convolution of two unequal length rectangles results in trapezium. Convolution of two, this one represent this one. So if you want to have discrete convolution, we can just multiply and just subtract and add it this one. So it will be discrete convolution. Correlation now. So I told you that if you do the integration with respect to dt, so you'll have the correlation. Correlation is measure of similarity between two signals. The general formulation of correlation is this one. Whereas convolution का full form क्या था? Is a mathematical operation used to express the relationship between input and output of an LTI system. It is only related to LTI system. It relates input and output and impulse response of LTI system. Like this. But remember these properties. The property number one is this one. You should remember. And if you do convolution with any delta, you will get this xt only. Shifting property also you can remember. 6t minus t naught, then next t minus t1, then it will be again shifted by t1, t naught minus t. So basically, if we have the periodic or the circular convolution, the periodic convolution is valid for the discrete Fourier transform because you will have the period. So to calculate the periodic convolution, all the samples must be real. The periodic or circular convolution is also called the fast convolution. If the two sequences of the length are respectively convolved using circular, then you can have this type of formula where 1, 2, 3 minus 1 minus 2, 2, 2, and it will be just multiplied by this value, this value, this value. So you will have the y by n as the convolution with hn. That is nothing but minus 1 plus 2, 0. This is 6, 3. This is 10. This is 6. It's great. And it is starting with it is having the length of 3 plus 3, 6. Okay. Again, whenever we have the correlation, we have two properties. Either auto correlation or the cross correlation. When it comes to same correlation of the signal itself. The autocorrelation of a signal is defined with the itself. The autocorrelation function is the measure of similarity between signal is time and its time delayed version. That is called autocorrelation. And you know, the Fourier transform of autocorrelation is function is what? Power spectral density. Okay. You have the Fourier transform of autocorrelation function is power spectral density. And do you know, if we have the power spectral density, how can we calculate the power of a signal?
Ma'am, integrating over all frequencies in power spectral density.
Okay, the area under power spectral density is actually the power. Very good. So tau is searching or scanning and a delay parameter. So if we want to find the similarity between signal and its time delayed version, that is called the autocorrelation function, the positive signal and negative shift. And the autocorrelation exhibits the conjugate symmetry. You will have this type with the symmetricity of this one. The autocorrelation function of the energy signal at the origin is equal to energy or the power. So autocorrelation at zero value is power or energy. Why? Because this is giving f. Sf is nothing but a minus infinity to infinity. If we represent this r tau, so rt dt e power minus j2 by ft. This is power spectral density. And the power spectral density or the R0, RT is nothing but the minus infinity to infinity SF e power j2 by ft dt. This is inverse Fourier transform. Okay. When RT equals to 0, so it is nothing but the minus infinity to infinity SF df. Sorry, df. Okay. So this is area under power spectral density is power. And this is equals to R0 is equals to power. Okay, that's why at t tau is equals to 0, it is power or the energy of a signal. Autocorrelation function is maximum. Let it be. But yeah, this is Fourier transform is power spectral density. And again, the autocorrelation function can be defined as a what do we mean by this thing? So yes, so as we know, the autocorrelation function, which is R tau, okay, it is not a function of t, it is a function of tau. Why? Because it is differentiated, integrating with respect to t. So you'll have the function as tau. So R tau, as we know, it's a correlation of any signal with its delayed version. Same signal. That's why it is called auto. But what if we want to calculate using the convolution? So it is equals to x tau convolution. This is convolution, not correlation, remember. X minus tau. So if you have any signal and if you convolve with the time reverse form, convolve, then we'll get the autocorrelation function of that signal. That is very, very important. How can we calculate the autocorrelation function using convolution operation? This we can prove actually. How can we prove? Because this is equals to, this formula is equals to x tau convolution with x minus tau. How can we have this formula? This is actually equals to minus infinity to infinity x tau. Convolution formula is what? Xt minus tau. So t plus tau, t tau. Okay, but here we are integrating with respect to t so that we are getting in the form of tau. Okay, so this is also same. Okay, convolution, the autocorrelation function of a power signal is this one, as we know. Okay, convolution correlation, density spectrum. So when we talk about one more thing, if we talk about Parseval energy theorem, energy or power flow. So what does it state that? Either power or energy calculated in time domain or frequency domain. Same. So you can calculate time of power, energy, time and frequency domain. So what does this mean? That even if we calculate energy is equals to minus infinity to infinity x t squared t is equals to minus infinity to infinity x f squared dt. Similarly, power, how will you calculate the power? How will you calculate the power? Power is nothing but 1 upon t, integration over one time period, integration over one time period, x squared dt. Okay, limit t10, t tends to infinity. Similarly, you can calculate summation or the integration over mod of xs squared there. So because since we can't assure that the signal in the time domain, wherever whatever the signal in time domain which is periodic, cannot or cannot be assured that it will be periodic with frequency domain also. So that's why we calculate Fourier series. Okay, so Fourier series is different from the Fourier transform in the sense that Fourier series is not a transform. It's just a way of representation of any periodic signal in the harmonics of sines and cosines. So the harmonics of sines and cosine is associated with one coefficients. Okay, that will be either even coefficients or odd coefficients. So odd coefficients are associated with the sine. Even coefficients are associated with the cos. So whatever coefficients, let's name it as a Cn. So the power can be calculated as sum of mod of Cn square n equals to minus infinity to infinity, where Cn is a coefficient. Okay. Now we will see at last the questions of page 9, because we are running out of the time. But yeah, we will see this thing, upcoming things in the next class. But it sounds so interesting to me. Just read signals and system and see some of the analogy in MATLAB. So stay tuned. You'll have some vectors manipulation. Then I think we'll have the Fourier series, Fourier transform. So sorry we couldn't reach by that time by this thing. But yeah, we should know some things that will be covered in the questions. Show the questions. Yeah, this was based on the question. Okay, so can you calculate the Fourier transform for on any signal? No, the Fourier transform can only be calculated for this type of conditions. The signal which have this type of condition, which is called Dirichlet condition. So function ft yeah. So function ft has a finite number of maxima minima, and there should be there must be finite number of discreties in the signal, and should be absolutely integrable. But the integration over all the time, so it should be less than equal to some finite value. Okay. Again, so Fourier transform xt is x omega, and if you want to have time shifting, so you'll have e power minus j omega t naught. So frequency shifting, you multiply with this one. So how I remember? So I remember like this, minus t naught, it's showing 2 e power minus j t naught x f omega. Then it comes here. So you'll have x plus f naught, and it is minus 2 pi f naught t. T is there, so T should be here. Okay, X. So if it is negative, it is positive. Similarly, it is positive, it's just negative. And time reversal is nothing but X minus T, X minus omega. So the upcoming things are very interesting. Sampling theorem, then discrete Fourier transform. There, some examples. I'll just jump to the questions of week 9. Last 8 questions. So given that a signal x1t to xmt are contained within a signal space, then there exists a basis with a cardinality. Cardinality means size of at most m that can be used to represent the same signal as vectors. What do you think? It is true or false? I don't know why my screen is not visible. Yes. The first question is, given that the signal x1t to xmt are contained within a signal space, then there exists a basis with cardinality of at most m that can be used to represent the signal as a vectors. What do you think? Is it true or false? The answer is, so actually, whenever we have the infinite duration signals or the signal space, so that will be again associated with the cardinality, and that will be again acting as a vectors. So that is very true. That will be true. Okay. The second question is, given a signal xt can be represented as vector x over an orthonormal signal space, then the energy of a signal xt can be represented as knob of, answer is this knob of x square. Norm of x square. As we saw also, whenever we have this, we calculated the integration over mod of xt square, right? So norm of x square. Third question is, a signal whose carrier frequency is much greater than its bandwidth is known as
Band pass.
band pass signal. Okay. Oh, very true. Nice. A low pass signal can have a non-zero central frequency that is much greater than its bandwidth. No, right? Because low pass signal will have the DC
Ma'am, I
frequency
think
as
it's
well.
false, ma'am.
It's possible. Can have non-zero center frequency that is much greater than bandwidth. Low pass signal. Center frequency, false. It is not possible actually. Why? Because low pass signal is a signal which shows that it is associated with the DC. Okay, it should be less than the bandwidth because that's why it is showing the low pass. After bandwidth, it comes to band pass. So it is false. Now, given an XF is a Fourier transform of real valued signal xt, then the magnitude of XF is function of the phase is, if it is real value signal, then a magnitude of XF is an even function, whereas the phase is the odd function. Even and odd. Answer is third, I guess. Even and odd, yes. Why? Because the magnitude spectra, if you see the magnitude spectra, it behaves like an even function. Even means XF is equals to X of minus F. Odd means phase of XF is equals to minus of phase of X of minus F. We'll see this more detail when we go to that part. But yeah, for now, I mean, you just remember this even and odd. Okay, even xt is a real valued time domain signal, and x plus t is a signal that only contains a non-negative spectral components of xt, non-negative. Then x plus t is non-negative spectral component. So we can divide any real value signal into two parts, x plus t or plus x of minus t, where x plus of t will be acting as an even. Okay, so I think that is real valued. Even means real valued. Complex valued, I don't know how. Complex valued is signal that only contains a non-negative spectral components. Non-negative spectral components of x t. Non-negative. Means what is only having the positive values. Okay, let's see. Given a low pass equivalent of a band pass signal xt centered around fc, it's represented as xlt is equals to pt plus jqt. Then xt can be expressed as low pass. So again, this is even and this is odd. So I told you the even can be represented as a cos and the odd can be represented as sine. So I think the answer will be, and again j will be replaced by negative. The answer should be C or first. Answer is negative, yeah. So why we are just multiplying the low pass equivalent? The low pass equivalent, why? When we multiply a signal with the cosine or the carrier frequency signal, then this is a real time, okay, and this is the negative. And we will see later that the cos have the center frequency as plus fc and minus fc, whereas the sine has the center frequency of plus fc and minus fc, but multiplied by negative minus 1 by 2. That's why it is negative. For now, you can just get, I don't know, uh, where we went. Okay, let's do last question. Oh, only 8 questions. So low pass equivalents can be used to analyze the performance of their pass band counterbalance. What do you think? Answer should be true. The equivalence in the sense is, see here also the low pass equivalent of a band pass signal we are doing using here. So it can be used to analyze the pass band. The pass band means the band pass thing. So answer is true. Then only we are doing the equivalent. Okay, so the answer is true. This was a week 9 of last year. Okay, solution was not given, but yes, the next week is digital communication. Next is again some digital communication, and the last week is again digital communication. So the next week we will start with some Fourier transform basics. Then we will I'll prepare some material on digital communication, which is ML detection, union bond, and all these things. I think. Thank you so much for joining. And I don't know why others don't respond. Used to respond. Raja, Keertana, are you appearing for the exam? Okay, so I don't know whether you guys are appearing for the exam. So Amber, you are appearing for the exam, right? Amber?
Yes, ma'am.
What is the score of you in these assignments?
Uh, just a minute, ma'am. Around 88 to 90, 90% actually. 88 to 90%.
Okay, very nice. So you can just expect that if you go score well in the remaining 4 assignments. So out of 12, only 8 assignments will be graded, right?
Ma'am, 6
So,
I have around 88 to 90%. And yeah,
acha.
not exceeding that actually, ma'am.
Okay,
And
okay, okay.
if that you question you told that na, if you can reevaluate it, then it will become 100, ma'am. My score
Okay, okay,
in that
sure,
week.
sure, sure.
So, yes, ma'am. And ma'am, actually, I have sent you a mail. Actually, a question. Uh, Ma'am, like I have studied about Hilbert transform in communication system. That ma'am, it's impulse response is ma'am 1/pi t, ma'am.
Yes, one
But
upon piety. Huh.
but ma'am, in that question, it is given which of the following is the Fourier transform. No, sorry, ma'am, impulse response of a Hilbert transformer. So in that options are not matching that the given actual answer, ma'am. So and ma'am, it is in ma'am week 9. So ma'am, like ma'am, I choose any of answer. May I think any of the answers are not correct, ma'am, in that. So uh,
Yes, yes, sir, that is well-known question. Hilbert impulse response that gives a phase shift, right? If you calculate the Fourier transform, it is plus 90 degree in positive frequency and minus 90 degree in
in
negative
yeah,
frequency.
in negative, yes, ma'am.
Okay, I will let you know. What is the question number?
I have sent you on mail. You can check it right now, ma'am.
You have just now sent. Okay, I didn't get the mail right. Okay, I'll let you know. Okay, no problem then in that case. Don't worry for that. Okay,
And
Amber, thank you so much for joining. Yeah,
thank
yeah,
you,
tell
ma'am.
me. Tell me.
And ma'am, actually, ma'am, last year some students told me that the final the CBT which they gave in offline centers actually. So the paper was not that much scoring. Like they were like it was, I think, new course. It was launched in 2023, I think. So they told me that na they like gave some questions like that in which there were 6 or 7 statements, and then you have to give like numerical answer type that how many of them are true. Then you have to write in box. So like ma'am, is there do they store like this previous year question like which came in the final computer based test? So we like
I
we
will
can
check with the
just
team, but I feel that if it is tough, then it will be tough for all.
okay, ma'am.
Uh, and I don't think that the score of that your this NPTEL should be considered in your thing evaluation. Like it should be like that you have completed as a credit. It should not be like
Uh,
that you got suppose 90% and
Earlier,
90% will be added.
ma'am, in actually, ma'am, first 2 years, ma'am, it was like it was of 0 credits. Now it is of like around 4 credit. It has credit points, so like na it will be used for giving me that GPA for that subject
Also
actually.
GPA. Okay.
Yes, ma'am. So
Okay. Okay.
like if yeah, so basically na like I have calculated that if like scored like around 88 to 90% in all 8 weeks, so I'll get an around 22 to 23 marks out of 25 in that final score, and
Yes, 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 yes.
the rest
Will be
75
based
it
on
will.
exam.
Yes, ma'am. So for rest, I'll have to make like around I have to score a total of score of 85% actually on certificate now to
Yes,
get
yes.
good GPA there. So there then out of 75 I have to get around at least 63 uh, in out of 75. The actual marks in that CBTs are of around 100, which means that I have to score around 84 in that out of 100
Yeah,
in
yeah,
the
yeah.
final CBT. So
And
that's
did
why
you
I
check
was
that the questions will be also based on MATLAB programming or something?
actually some actually no they were given statements, and now we have to like um somewhere like around of numerical type. Like actually no I don't know the exact question, but some students who gave last year I know some of them. So that was not very much scoring. When we I think highest was around 87%, I think. The toppers list I saw in that, and
Okay. So
some of my
you can also try mailing to the uh, community that is created for the this subject, simulation of communication system using MATLAB. Rest, I will also try from my end.
Ma'am, which book, ma'am?
There should be discussion forum or the group.
Okay, ma'am. Discussion forum. Yes, ma'am.
Yeah.
Okay, ma'am.
It is there for almost all the subjects in
Yes,
NPTEL.
ma'am.
So you
Yes,
can
ma'am.
try joining that, and you can try mailing to the group also. So that you'll have the friends also. Try to score well in the assignments. That should be good enough. And
Yes, ma'am.
if, as far as I know from the final exam part, it
Yes,
will
ma'am.
not be very tough. Okay,
Yes, ma'am.
there could be some confusing questions, but it would not be very tough.
Yes, ma'am.
Sorry about that.
Okay, ma'am.
Okay, Amber, thank you so much. Yeah.
Thank you, ma'am. Thank you, ma'am.